Hello everyone, my name is Ibrahim and I am going to present a paper on evaluating the feasibility of predicting information relevance during sensemaking with IGES data. Let's start with an understanding of what sensemaking means. It's a task that involves gathering information from various resources, extracting special insights from them, generating a hypothesis, and finally telling a story. And the whole process is not necessarily linear. It's a loop, as described by Perry and Kurt, where the more effort you give, the more structured your story becomes. There are plenty of analytic systems out there to facilitate the sense-making task. Still, it demands heavy cognitive effort from the analysts. The Space to Think project from North et al. Showed how semantic interactions can provide intelligent assistance to reduce this cognitive effort, but that has been limited in large 2D displays. There are two things we can take from here. First, sense-making tasks require heavy cognitive effort. Second, sense-making tasks require analysts to browse through multiple documents that are interconnected with each other. We propose an intelligent immersive analytic system that can observe the analyst's eye gaze data and infer their intent, anticipate what they're thinking, provide relevant, meaningful information based on that observation. Now we can get more than 100 measurements from a user's eye. However, according to prior work, gaze duration and unique dwell have been most successful in inferring users' cognitive process when it comes to reading a single document. Let's walk through an example of how it works. Given a document, when you read it, there are certain words that attract more attention from you than the others. If we just consider the amount of time spent on each word, or the number of times a word has been read, this is one of the possible outcomes where red means more time and green means less time. So this is what the list looks like when I have just read this single document. Let's see how this list changes when we start reading more documents. Here, the word date jumped up one step because it's also on the second document. The word Springfield went lower even though it may be more relevant than the word date. So what happens when you read more documents? The word date ends up climbing to the top, not necessarily because it's very relevant in this context, but because it's just in very high frequency and it's capturing the reader's attention every time they read a document. This introduces an issue in multiple interconnected document datasets called frequency bias. This is the data from SenseMaking session with actual user. We asked them to write down the top 10 keywords that they think are relevant to their SenseMaking task, and this is what they came up with. On the side, you can also see the list of words sorted by the amount of time spent on them. As you can see, there are only 3 words that matched with the user's perception. The takeaway here is that gaze duration or number of dwells on a word cannot really address the frequency bias issues when there are multiple documents involved. So, we need to figure out how we can use the gaze data to infer user perception in a sense-making task. Similarly, documents with more words naturally require more time to read, which introduces a length bias. We also need to address that when we are trying to use the gaze data. This brings us to our first research question. How can we design a metric based on the case data that can correctly capture the user perceived relevance of words and documents during sense-making with multiple documents? To answer this, we asked actual users for their opinion on lists of words created with different metrics. What we came up with are these 3 considerations that are required for an effective case metric. First, we need to normalize the case data to remove the frequency bias for words. Second, we need to normalize the case data for documents to remove the length bias. Third, we observed that sometimes the relevant documents have high gaze duration while other relevant documents have high number of dwell counts. So in a dataset with different types of documents, both of these measurements are crucial in capturing the user's perception of relevance. So we need a metric that combines these two together. Our final output is a metric called GazeScore, where the first part handles the normalization of documents and combination of the two metrics, while the second part is a weighting factor IDF, widely used in the NLP technique to address the frequency bias. Since different people have different reading speeds, the gaze score can be pretty arbitrary, which makes it difficult to compare among participants. So we'll also use gaze rank, which is just the index of a word or document after sorting them based on gaze score. Our second question is, to what extent does this metric predict the relevance of documents and words? In other words, how successful is it? To evaluate that, we conducted a user study with 12 participants. They all used the HoloLens 2 with eye tracking enabled. We used the sign of the Kirsten dataset that had 24 documents containing information about 2 potential terrorist plots. The user's task was to investigate the documents and figure out the who, when, and where of these 2 plots. While doing so, they could create notes, labels, or search the document for words. We collected data on 2 ends. During study, we calculated the GazeScore and GazeRank for all documents and words based on the user's iGaze behavior. After the study, we collected the user's perception of the dataset. First, they freely reported documents and words that they found relevant in their investigation. Second, we showed them documents and words with different levels of gaze ranks and asked them how relevant they were. We'll discuss them in detail in the next few slides. For free response, we had the participants pick out 4 documents and write down 10 keywords that they found most relevant to their investigation. We call them free response documents and free response words. During analysis, we derived the case ranks for these documents and words. Looking at the histogram of these ranks, we see a downward slope for both documents and words, meaning that most of the documents and words were high on the case rank list. We also see that 38% of the documents were in the top 4, while 19% of the words were in the top 10. The random chance to be the top is much less than these numbers. We also had the participants rate 12 documents and 30 words, all with different case ranks. They were randomized before showing to the users. The users rated them based on their relevance, complexity, and for words, familiarity. We found no effect of case data on either complexity or familiarity, so we'll present our result on only relevance. We found that both documents and words with high case ranks were also rated as more relevant by the users, meaning the case data could predict the user perceived relevance of the documents and words. Overall, we found that the relevant documents and words had higher GazeScore than irrelevant documents and words. That brings us to our last research question. Now that we know that the iGaze data can be used to infer users' perception of relevance, how can we use it? How can we use it in a real-time sense-making task to improve the intelligent suggestions to analysts? I'll discuss a couple of ideas here, while the rest of them can be found in our paper. One use of the case data could be to externalize the mental concepts of the users by visualizing their case data on the documents. So, at a glance, they have an understanding of the content they are interested in. This can be particularly useful when the user is working on a dataset with hundreds of documents for weeks. This information may eventually be used to look for more documents from the unread pool that the user might find interesting and bringing them closer. So, final takeaway. Before using a case metric, we need to make sure that it's not susceptible to any bias from the dataset. Second, we found out that we can infer user perceived relevance of document words from iGaze data during sense-making tasks. We also demonstrated ways how gaze data can be used to build towards an intelligent immersive analytic system with externalization and smart information retrieval. Thank you for listening.